In this video, we introduced the idea of a non-ideal power source and the terminal voltage of the non-ideal power source. So until now, we've treated batteries as if they have no internal resistance. In fact, all batteries have some amount of internal resistance, and we can model any battery as an ideal power source, sometimes called an EMF or electromotive force, in series with a small internal resistance. Now the nodes that we've labeled here in the circuit, A and B, those are the actual battery terminals. If the battery isn't connected to anything, then no current can flow. And if we put our multimeter across these nodes A and B, we're just going to read exactly the same voltage as the EMF that's being maintained by the chemical reactions in the battery. However, when we connect this battery to a resistance, and I'm calling that the load resistor in this case, then I'm going to have a current flowing through the circuit. And that means there's a current flowing over the internal resistance of the battery. Well, Ohm's Law tells us that if a current is flowing over a resistor, we have a voltage drop. And this means the voltage between A and B is going to be less than the ideal EMF. So the way we sort of formalize these voltage differences is I would take a path from one node to the other, and I'll say the potential at A plus the EMF as I'm traversing this path up the left branch of the circuit. I just went up by a voltage equal to the EMF minus IR. So I applied Ohm's Law there. I said V equals IR for the resistor, and that was a voltage drop. So VA plus the EMF minus IR is equal to VB. This allows us to express VB minus VA as the EMF minus IR. And this difference, VB minus VA, that's the voltage across the terminals of the battery, and we call that the terminal voltage. Sometimes we'll use a VT for that. So we finish with a typical example of how you might be asked about the terminal voltage. We're told that a battery produces an EMF of 9.0 volts and has an internal resistance of 0.1 ohms. My software automatically turned that into 100 milliohms, but we'll just change it back. And we want to compute the terminal voltage of the battery when it's connected to a 47 ohm load resistor. So all we're going to do here is simplify the circuit to have a single resistor, and then we're going to find the total current, and then that will allow us to find the voltage drop over the internal resistance, and we can get our terminal voltage for the battery. So we'll redraw the circuit with a single resistor. All I have is two resistors in series, so it's just an R1 plus R2 kind of thing. And again, 100 milliohms is just 0.1 ohms, so when I add these, I get 47.1 ohms. Now I apply Ohm's Law, and I say that I is equal to V over R for this. That's 9 volts over 47.1 ohms. And I find that 0.191 amps are flowing through the circuit. If I then go back to my original circuit, I have I equals 0.191 amps. And then I can get the voltage drop over the internal resistance and get my terminal voltage. So my terminal voltage is going to be the ideal voltage of 9 volts minus the voltage drop due to the current over the internal resistance, 0.191 amps times 0.1 ohms. Sometimes that's called an IR drop because we just took current times resistance to get it. And I get 8.98 volts out of this. So again, anytime you have a battery that's actually running a current through a circuit, the terminal voltage on that battery is going to be less than what it is if it's not connected. And the bigger the current that you're running through the battery, the bigger the drop over that internal resistance. So the terminal voltage is going to drop. If you find the physics content on Zach's Lab helpful, click on the Zach's Lab logo on the right to browse playlists and subscribe to the channel. I produce over 100 new videos per month, and subscribing is the easiest way to find new content. Thanks for watching.